Welcome to unit number 4 of the Illustrated Guide to the National Electrical Code. And this one is dealing specifically with just cables. There's different types of cables that we have to look at. There's non-metallic sheath cabling. There is BX cabling. So we have a lot of different types of options for us to run electrical conductors that are already enclosed in some type of coating or jacketing so that they are used for specific locations. And the code helps us to understand that. Where can you install NM or non-metallic sheath cable and where can't you? Where can you put in a metal clad type cable or BX or MC cable at? And so we're going to go through those in this chapter and give you a better understanding and hopefully be able to open up the code book and make it a little bit more easy to understand as we talk about the practical applications. So let's go to the book now. Okay, so we're back at the book here, and now we can take a little deeper dive. Now, we've got two options for framing, and in Southern California, we're going to be using wood in most all residential, some commercial, some schools, and steel framing for mostly commercial, industrial, some schools, and very rarely do you see this in a house. It's possible. So the difference between wood and steel is that wood will either need to be punched with one of these punches right here. It's a special punch, knockout, that you would punch the hole in the steel, or they come already pre-notched and have holes in them to run multiple BX cables through. Now, we don't use a non-metallic cable in steel if we can help it, but if we do, we need to put a non-metallic sheath cable grommet into that hole where it snaps in. So this hole size and this piece, they're made to be worked together and they snap in. And so we do use non-metallic sheath in steel studs. We have to make sure this is there. Why? I'm sure you answered that question really quickly. Metal and rubber jacketing or plastic jacketing is going to wear by moving back and forth by vibration. So we definitely need to protect it. Now this is an important one right here. Setback for boring. Holes must be bored so that the edge of the hole is not less than 1.25 inches from the nearest edge of the wood member. This comes from 300.4 A1. Now, why 1.25 inches? Well, the normal drywall screw size is going to be 1.5 inches for 1/2 inch drywall. And that is 1.5 inches, gives you 1/2 inch for the drywall, and then 1 inch for the set, and then if it goes through, gives you another 1/4 inch for that drywall screw not to penetrate into the bore hole where your cable is. For 5/8 drywall, it's 1 5/8 is the screw size, and again, that gives you 1/4 inch of variance. So you need to be in the center. Now, this applies to studs, joists, rafters, etc., any framing member. Now, again, I will share with you as much of my mistakes as possible so that you don't make those same mistakes. Mistake number 1, make sure that if you are going into a joist, which is going to go across hold the ceiling up, that you talk to the carpenter and make sure that you are not going to weaken the wood framing member by drilling holes in it. There are some cases where the carpenter doesn't intend for any holes to be drilled and therefore sizes it just the way it is to hold it up. You start drilling holes in it, now you've weakened it for that span, the length that it's got to hold up. So these are some considerations. If you have to drill it, which in an attic space you don't, but if you're down in between the 2 stories, you're on the first floor, and you need to go through those joists, then you need to work with the carpenter to make sure that they have accounted for you putting holes in the framing members. Now in the newer homes, they're using an engineered beam. Engineered beam uses a OSB plywood with wood on solid wood on top and bottom, and there's actually knockout punches there. You take a hammer, you knock it out, and it puts it right in the center of that beam. They're pretty trick. They work great for the newer installations. Now what happens here, now look in this case right here, what happens when you have to notch the stud, or you can't bore it you can't go to the center of the framing member and you have to go out there? Well, we need to put in they call them nail-on plates, protector plate. We call them nail-on because they just nail right on, and there's two different sizes here. So there's this one here is found in the plumbing section. This one here you find in the electrical section. Now, I usually will get both and keep both with me if I'm doing a job, because I want to make sure that I can cover a larger notch or a larger section of pipe. These are bigger for plumbing, obviously, so you don't put a screw through it. So these are available, nail-on plates, and these go on to the stud to stop a drywall screw, or later somebody hanging a picture to put a nail or a screw into the wire. I've actually known people that have accidentally done that and caused themselves a huge headache. Now, if you put in, so B here says cables installed in a groove covered by wallboard, paneling, carpeting, etc. shall be protected by 1/16 of an inch thick plate steel. Okay, that's this right here, 1/16 of an inch thick. Sleeve or equivalent by at least 1.25 inches of free space for the full length of the groove which the cable will be installed. Now F says when you have to notch the members, you can put a plate on there by just notching it. And this is a technique that I have used before on 2-story homes. When you want to run additional lighting, you notch it, and then you put in a nail plate over that, and that way you don't have to continue trying to pull it through the ceiling space. Now, when parallel to framing members and first strips, so this is an example of where the cable is running parallel with the framing member, and it needs to still be 1.25 inches from the sides, even if it's running on the parallel to it, on the outside, nailed to it. Now, the easiest way to remember this is just go right into the center of the stud, whether it's a 2x4, 2x6, 2x8. You go to the center, you'll be fine, you'll meet it. This is based upon a 2x4 construction. Now, some penetrations going into through fire-rated floors or ceilings or walls, you need to use a fire stop caulking. That fire stop caulking will expand and keep the flames from going through between the levels of the building. Mostly you're going to find that, like I said in the last video, is going to be within a condo complex, an apartment building, any place where you have shared walls and multiple family residents are built in there. Now, securing the cables right down here at the bottom, securing the cables for MC cable, we can go 12 inches and then 6 feet. So 12 inches and 6 feet for MC cable. This is the metal clad cabling. Looks like a flexible metal cable. For AC cabling, it's 12 and 4.5. AC cabling is used in some places, and others you're not allowed to use AC cable. Non-metallic sheathed cable is 12 and 4.5. And then from a non-metallic box, you need to go at 8 inches from the box to your first location. So be careful when installing what type of box you're using. You want to make sure that you're secured properly. Now, if you remember that the plastic box that I showed you has these push tabs in there, and that's all that's holding it in. That's all that's restraining it. So that's why you need to be 8 inches. Now you can go up to 12 inches because on the metal boxes you're going to be using a 2-screw connector, or you can use that fancy connector that I showed you here that plugs in and restrains it as well. Now this is probably take you to 8 inches, not 12, just to give you just kind of a precaution there. So on AC cable and MC cable, there's a specific radius over here that we have to be careful of. And the reason why is because if we bend this at a sharp 90, it will break this open and you will expose the conductors and it ruins it. So this radius is important. And in 320.24, the bend radius is 5 times for AC cable. MC cable is 7 times, and that comes from 330.24b. Non-metallic cable is going to be a bend radius of 5 times the diameter of the cable, and that's 334.24. I encourage you to go look at all of these code sections as you go through and take your time with it. So I want to show you a couple different variants of non-metallic cable. Non-metallic sheath or NM cable has this nice thick coating on there, and inside we have our conductors. The ground is always bare, and it's jacketed with inside of a cardboard or paper type jacketing on the inside here. This is a non-metallic sheath NM 12-2. It's 12, number 12 AWG, and you don't count the ground. It's only 2 conductors, gives you a 12-2. So we're only counting the current carrying conductors on non-metallic sheath cable. So why do I know this is 12 right out of the gate? Is because I know that this one is 14 because 14 is white, yellow is 12, and I believe orange is number 10. So it makes it very easy for an inspector to see it. It makes it very easy to track for the electrician to know that I've got number 12 going to convenience outlets in the kitchen, and I have number 14 going to my outlets in my bedrooms. So it's very easy to differentiate. But again, this is non-metallic sheath cable, 12-2 conductor. Now, variation of this, what size is that? 14. It's white. So this is a 12-3. We have 1 neutral and 2 hots. So 1, 2, 3, 12-3 with the bare ground. And so this is used for going into, say, a switch where you've got 2 switches going up to 1 fan, and you want one of the switch legs to run the fan motor and you want the other to run the light. And so you would run this down, and you have to have a neutral inside your box for all lighting boxes. And you can get it even larger, and it goes even larger than this. So again, now our jacketing is not the same. So our jacketing kind of goes out after 14, 12, and number 10. But this is a 8-3. So this is number 8. And if you're not sure, you can always look at the side of the cable here, and it'll tell you what the cabling is. And so this is a number 8 gauge wire, and there's 3 of them, so it's an 8-3 Romex with a ground here. So these are all sized and ready, but you'll notice that not very pliable, can't bend it very much. So when you take the 5 times the radius, this is about say a ½ inch, and so you multiply 0.5 times 5, and that would give you the bend radius, but you physically can't bend it very much, so it's pretty stiff. This would be good for connecting air conditioning units and some ovens, depending on the size. Now, when using an AC cable, you need to use what is called an anti-short bushing. And this is what the anti-short bushing looks like, a little piece of plastic. This tab must stick through. So right here it says that some insulation from the anti-short bushing on manufacturers of a part of the bushing that extends past the connector or clamp once installed and effectively acts as a flag. This flag must be visible. And so an inspector may open a box up and look, and they want to see this sticking out. They want to make sure that you put that anti-short in, because if you can't see this, they don't know if you put it in or not. So make sure this is sticking out of the connector. The connector has slots in it as it goes around, and it'll stick through there. But the anti-short installs just as you see here, and it's intended to protect the wire from the sharp edges of the AC cable. Now, whenever we're running an exposed non-metallic sheath in an unfinished or crawl spaces, we want to make sure that it's completely nailed up and not just laying on the ground or laying in an attic. It needs to be completely secured along that entire run. Now, you can use NM cable like this if it's protected. If it's in a garage, if you're in an attic space or a top space there, you can get away with running that cabling because it's protected. It doesn't take much to damage this. Now, if you're down below and you're down below where you need to make sure that it is still protected, then you need to go to an AC cable or put this into conduit to go down to a box. You can put this in a conduit, but I don't recommend you pulling it through a conduit. A straight run, it'll work pretty easily. In PVC pipe, it will be a nightmare because this jacket acts as a brake as it slides across the plastic, and it also doesn't go through 90s very well. But if you need to chase it through a wall or go down to a receptacle to protect it, no need to change the type of cable, just go straight through and you can put this in a conduit. Just don't try pulling it. So again, I'm saying you can do it in a conduit, but just do it straight. This is the example of that. And you can put it into this this run, and it says cables entering or exiting a conduit shall be supported or protected against physical damage, which requires fittings on the conduit and tubing ends to prevent from abrasion. So it's not just the cut conduit at the end, it's got to have a bushing. They make a bushing that goes straight onto the end of the conduit. It pushes right on, so you don't need to buy the connector and the bushing to go on there. Now, conductor identification. So when we need to make sure that the conductors are identified properly, that the white conductor is being used for the neutral and the red and the blacks can be used for the hots. And of course the bare ground is going to be the ground. So in an AC cable, it's a green wire as the ground. Three-phase identification in cabling is typically going to be black, red, and blue. And your neutral could be white, it could be gray, or it could have a stripe on it. And your green could be green or green with a yellow stripe. Now when you're using the white conductor as a grounded switch leg loop, it is possible to use a 12-2, and you're going to then make the white the switch leg. The hot is always the hot, but going between this receptacle, for example, in this picture, takes a neutral to this receptacle, and then you have a hot going to one side, and then you pigtail this and you take another hot on the white, but it's taped red, and you tape it up in the box, but you can use the white of a 12-2 here instead of having to get a 12-3 out. There's no need to get a 12-3 just to have two colors here. You can use a 12-2 to do that, and you just need to tape off the white as red when it enters the box. Now, it used to not have that red requirement, and that was very confusing when you were at a switch, but you're only at a switch. At the time, the switches didn't require neutrals. Now the switches require a neutral. So this may not actually even be correct in some applications, depending on what you're trying to do with it. So you may always need to have a neutral there in all applications. Not every one of them right now is required. But if we're going to use the white as a hot, we need to tape it up as red to identify it. And so we can see here that we're taking from the switch, we have our neutral, and we are capping off our neutral in the box. And so it says the grounded circuit conductor. Grounded conductor is a neutral. It's not the ground, green, grounded. So go back to the definitions. And it says when a grounded conductor for a controlled lighting circuit is not required where multiple switch locations control the same lighting load, such that the entire floor area of the room space is visible from a single or combined switch location. In this type of installation, the grounded circuit conductor shall be required at one location. So we can feed coming in with just 12.2, and we leave coming out with a 12.3 because we're doing three-way switching. We need two travelers and a neutral. We have our neutrals at the box to make sure that they can be accessible by some devices. And then we're going to use a 12.2 going up to the switch. So 12.3 between the two because we need to have the travelers and the neutral at the locations. And then the grounded conductor provided for the future. So we need to make sure that we have a grounded neutral conductor. And it says, although the grounded conductor will not be utilized in the current design, this design here, it must be provided that at the switch location unless meeting one of the exemptions of 404.2c. Now, new construction, it requires this for the future because there are smart controlled switches, dimmers, and timers that require neutral in order to be installed. So if you're doing a job where it's an older construction and they don't have a neutral, you have to buy a switch, a smart switch that can be used without a neutral. So it's really important you look at the type of switch. Some can and some can't. Most of the new ones now on the Wi-Fi connected smart switches are requiring a neutral, has to be there. So it really is a limitation for some people in older homes that did not have that construction. There are some direct burial cables available. The utilities used to use these cables to install services from the handhole box to the house and where it went up into the house. We have most utilities in the West Coast moved away from this because when they go bad, there's no way to pull in a new one and you end up paying for it later. It's cheaper to install now, but you pay for it later. Preferred to have a conduit in there. So the feeder cabling that can be pulled in has specific depth requirements here. I wanted to just point those requirements out because it depends on where you're at. Street, highway, anywhere where a parking lot or a car drives over, it's 24-inch minimum depth. However, if you're, for example, over here, locations that are not specified in 305.5, then it's going to be 12 inches minimum. And so how far down can you go? Maybe you can't get to 24 inches under the road bed and you have to put it in conduit to protect it, and then that changes your depth requirement. And so just want you to see the differences here. Low voltage cabling, which is not more than 30 volts. This is outside lighting. You have to go 6 inches minimum for that type. And if it's in conduit, it can go to 4 under a slab. So again, this is to protect the cable from being damaged by the weight or pressure from above. And you need to be at the right and proper depth there. So for the minimum cover for residential branch circuits and in or under airport runways that are adjacent areas where trespassing is prohibited, it's 18 inches. And you would go to 305.5 for that information. So let's just look at that really quick. Okay. 300.5 is this section right here, and in this section, so we're table 300.5 minimum cover requirements for up to 1,000 volts. And so we're going to find our location. All locations not specified below. Okay. How about we're under a building? So we go to this one here. We're under a building, and it's going to be 0 inches because we're underneath the conduit. I'm sorry, we're underneath the concrete. Now, if we go under a street or highway, we're at 24 inches. For direct burial, for rigid metallic conduit, we're 24. For non-rigid metallic conduit, we're 24. So it's 24 straight across the board under roads. Now, under roadbeds can be much thicker than 24 inches, depending on where it's at, especially highways. And we don't want to be in a roadbed where it's going to get damaged. So there may be requirements for that transit authority or for Caltrans, for example, in California, that we would have to be deeper than that to go underneath the roadbed itself. And so this table here is telling you what those minimum requirements are, and that is to the top of the conduit. I want to point that out. This minimum requirement is the top of the conduit, not the bottom of the trench. And so if you're running a 24-inch deep minimum, that's to the top of a 4-inch conduit. That means your trench depth is a minimum of 28 inches. And if you're then sitting on top of conduit spacers, or we call them chairs, they're plastic pieces that hold it up because you're gonna backfill it with concrete, then you have to account for that. So just go to the top of the conduit. And if it's multiple conduits on a duct bank, it's always the top conduit of the duct bank that you need to measure to. Medium voltage cabling is a little different. This is 2001 volts or greater. And then that cabling design, as you see right down here, has multiple layers to it. Starting at the center, we have the annealed copper conductor. We then have an extruded shield on top of that. It's like a plastic shield on there. Then we have the ethylene polyolene rubber insulation, so the EPR. This is the EPR here. And then we have an extended insulation shield. Extruded insulation shield. And then we also go to a copper shielding tape. So this could be tape, or it could be individual strands of conductor. So it just depends on the manufacturer, depends on the utility, depends on the requirements for that location. But the shield and or the concentrically wound bare copper wires around here act as a shield for the cable. Then you have a black PVC rubber jacket over that. So to terminate, you have to strip back appropriately before you can terminate the special end on there. High voltage cable terminations are a specialty, and you have to be certified in terminating these types of cables. So that's all I've got for you for unit number 4. We've covered almost everything in this chapter, and I hope that it gives you a good understanding of the different types of cables that are used in the industry and how we might use them. So again, read through the book. Make sure that you're going through what it tells here as you're following. For example, A goes to A. Okay, what does it say about that? And read the notes and help this digest it. So if you're reading it, you're hearing me talk about it, then you're writing about it, you're answering questions. All of that is to help you remember it, which is the most important thing you need to get out of the class. So get your homework done. Again, on the homework, you're going to need the NEC reference, and you need to put the answer in. So you need both of those for answering these sections here. All right, take care.